But I will post B. It's very similar. I think there are already 2 videos of me going through that mechanism, and I'll post it. But I do want to look at the second one, which is actually from the assigned homework problems, which is problem 23.45, which is that synthesis problem. We're probably expecting a synthesis. CHO obviously is an aldehyde, so I'm going to draw that out as the aldehyde. And other component is this alpha beta saturated ketones. So there's compound A and compound B. And we want to devise a synthesis that starts with these 2 and ends up with compound C.
Inside of the 5-membered ring, there should be an O.
There's lacto. I think I got that on the key too. Probably know. The O is not actually relevant.
Well, I know.
So we're trying to make compound C. There's a new bond here, and that's between what used to be the aldehyde carbon. And the 4 position of alpha hydroxide ketone. So we're trying to make a new bond between these 2 carbons. Obviously, this is an application of the acyl anion equivalent. We need to make this carbon negative so it can attack the partially positive carbon of the alpha beta unsaturated carbonyl. So that is an application of the dithiane. So we're going to use 1,3-propane dithiol with a loose acid catalyst. 2 we talked about, not the only 2 you could use, but the 2 we talked about, chloride, trifluoride, or zinc chloride. Both of those will accomplish this. And that'll make an additional 6-membered ring. And convert the proton, which wasn't acidic at all, into aldehyde proton or not. Right? Let's start recording this again. Right? So now we have the acidic proton, but we need a pretty strong base to take that off. Standard base, removing that is going to be lithium. So we'll take that proton off and generate the lithium anion. Here's my acyl anion equivalent. Which behaves like an aldehyde negative charge without being an aldehyde negative charge. Most of the time, alkyl lithiums, when they add to alpha beta unsaturated carbonyl compounds like this lactone, add directly to the carbonyl carbon as a 1,2 addition. And if we wanted a 1,4 addition, we'd have to use a cuprate. So the question is, why do we not have to use a cuprate in this case? Why do we get a 1,4 addition? It's obvious you do get a 1,4 addition because you can see where the new bond is made. So what's special about this compound that causes the 1,4 addition?
The oxygen has a partial negative charge. Like when you drew it out.
Which oxygen?
The carbonyl one.
Yep.
So attacking it wouldn't really make sense, would it?
Attacking the oxygen wouldn't make sense.
Oh, sorry.
But this carbon has partial positive as well. Right? Because there's 3 resonance structures. There's the resonance structure that just has the charge separation here. That double bond is still in place. And there's the resonance structure. Put the positive charge down here instead. So we've got a choice. We've got 2 carbons that have partial positive. Usually, alkyl lithiums attack the carbonyl. Right?
Right.
Cuprates attack 1,4, and gradients can't make up their mind and attack both. So there's something special about this alkyl lithium, because this alkyl lithium is doing a 1,4 addition, and the 1,4 addition is not usually what we see for alkyl lithiums. Right, so we've got as our product that. propane with H. Plus water is going to generate
Is it a stability thing?
it is a stability thing. Okay. And then all we have to do to generate the final product from this, pure chloride, water, sometimes acid carbonate, and that chops the dithiane back off. So it's a four-step synthesis. Put the dithiane on, put the dithiol on to make the thioacetal. Take off the acidic proton with then lithium. Attack the alpha beta unsaturated lactone, protonate, and then use mercuric chloride to take the dithiane back off. So effectively, we're using the dithiane as a protecting group to make the aldehyde not look like an aldehyde, so that we can remove that proton and make it acidic. And it does a 1,4 addition because of the stability thing. This anion is significantly more stable than this anion, for example, which isn't really a complete anion anyway. We've got about a plus 0.4 charge on lithium, about a negative 0.4 charge. That bond is about 40% ionic, 60% covalent. So we've got a significant negative charge on here, though it acts like the butyl anion. And the butyl anion is a lot less stable than the dithiane anion. So the question is why? Which is basically the same question as why is this now acidic?
The sulfur is electron withdrawing.
2 electron withdrawing sulfurs are pulling electron density away and stabilizing that negative charge. What that does is make it a lot softer. That negative charge is actually spread out, not just on this carbon, but over the 2 sulfurs as well. And it's benzylic. So it's also possible to write resonance structures to this, and then put that negative charge in the ring. You can write a resonance structure and write the negative charge here instead by moving that pair of electrons here. And you can write 2 more that also put the resonance structure on those other positions. And that's why hydrogens that are in benzylic positions are also more acidic than hydrogens that are not. So we've got several things that are stabilizing this negative charge, softening it up, and a softer base is going to do a 1,4 addition. So that's somewhat surprising. And it's the reason I assigned problem 45 in the first place. You understand that there are many different ways of softening an anion. One is making a cuprate, so you make the bond less ionic with this bond, but the other is putting electron withdrawing groups that will stabilize it inductively, or, in the case of the benzylic or the amylic position, by resonance. And resonance stabilization is the best. If you can get resonance stabilization, that stabilizes things more than an inductive effect, because that actually allows the negative charge to spread out over a larger portion. And remember that every electron secret goal in life is to occupy all space simultaneously. So the more the electron can spread out in space, the happier it will be. So that's the quiz.